Circuit elements may be connected in series, parallel, or both. And here we'll look at resistors in series and parallel, specifically in compound direct current circuits where the current flows in one direction. So if we have an EMF produced by a battery and using conventional current, we have the current flowing in this direction. And because we have the resistors in series in this case, the charge passing through one resistor must proceed through the other resistor as it has no other path available. So therefore, we have the current is equal to the current through resistor 1 and also through resistor 2. So what's different is the total voltage drop across both resistors is equal to the sum of the voltage drops across each resistor. So that will be delta V1 plus delta V2. And now we can apply Ohm's law. So the voltage drop is equal to the current by the resistance. So therefore, we have the voltage drop being the current multiplied by the equivalent resistance of the resistors in series, which is equal to the potential drop across the first resistor plus the potential drop across the second resistor. So as we can see, because the current is constant, it cancels, and we obtain a general equation that the equivalent resistance of a group of resistors in series is equal to the sum of the individual resistances. So if we have n resistors, we add the resistances of each resistor to get the equivalent resistance. So effectively, we can analyze a collection of resistors as if it were a single resistor with an equivalent resistance being the sum of the individual resistances. Now in the case where we have resistors in parallel, then the current has several paths to flow. So in this case, it's going to branch off into the first resistor and the second resistor. So by the conservation of charge, the current is equal to the sum of the individual currents through each branch. And in this case, the voltage drop across the group of resistors is equal to the voltage drop across each resistor. So the voltage drop is constant. And now applying Ohm's law using this equation, we can write Ohm's law as the current being equal to the voltage drop on the resistance. So therefore, the voltage drop across the group of resistors on the equivalent resistance, which we'll call Req, being the equivalent resistance of the group of resistors placed in parallel. And that's equal to I1, which is the potential drop across the first resistor. So this is constant and equal to the potential drop across the group. So we have delta V on the resistance of the first resistor plus delta V on the resistance of the second resistor. And as we can see, delta V cancels. So we have the reciprocal of the equivalent resistance of the group of resistors in parallel being equal to the sum of the reciprocal of the resistance of each resistor. So here, we're summing over the number of resistors that we have in parallel. Now, because the resistors are connected in parallel, the number of paths available for the charges to flow increases, and therefore the equivalent resistance of the group of resistors decreases. And we'll see that in example problems. All non-ideal or real batteries have some internal resistance. So when this resistance is negligible compared to the resistance of the elements in the circuit, we neglect it. And the same goes for wires. So because they're good conductors, we can neglect their resistance if the circuit contains other elements that have resistance, such as resistors in this case. Now, the potential difference a battery would supply if it were ideal, so with negligible internal resistance, is the potential difference measured across the terminals when there is no current in a battery. So this is sometimes referred to as its electromotive force. Now, for a non-ideal battery, we treat the internal resistance as the resistance of a resistor that's in series with the ideal battery and the remainder of the circuit. Now, when there is current in a non-ideal battery with internal resistance R, the potential difference across the terminals of the battery is reduced. So that would be the electromotive force of an ideal battery minus the current passing through the battery by the internal resistance. So the potential difference across the terminals is reduced relative to the potential difference when there is no current in a battery, such as in the case where this circuit is open. So we refer to this as the terminal voltage. Recall that ammeters were modeled using the following symbol. So ammeters are used to measure the current at a specific point in the circuit. So the ammeter should be connected in series with the element in which the current is being measured. And ideal ammeters have zero resistance, so they don't really affect the current in the element that they're in series with. So for example, this resistor. Now voltmeters, on the other hand, are modeled as follows, and these are used to measure the electric potential difference between 2 points in a circuit. So voltmeters must be connected in parallel with the element across which the potential difference is being measured, such as this resistor in this case. So if we want to measure the potential difference across the terminals of the battery, then you put the voltmeter in parallel with the battery. And ideal voltmeters have an infinite resistance. So effectively, no charge flows through them. So by putting the voltmeter in parallel with this resistor, we don't create another pathway for the current to flow. Now, non-ideal ammeters and voltmeters will change the properties of the circuit being measured. And this can be seen for the ammeter. When it doesn't have negligible resistance, then you're going to have the potential drop across the ammeter being non-zero. So it'll alter the current in the circuit. And if the voltmeter didn't have an infinite resistance, then the current is going to flow through both branches here. So it draws current away from the circuit. Consider the following circuit, and we're first asked to determine the power dissipated as heat in each resistor. So using conventional current, the current's going to flow in this direction, and it's going to be the same across this first resistor, and then branch off into two different currents through the second resistors in parallel. And then by the conservation of charge, the current in is the current out, and it's constant throughout the rest of the circuit. So now let's copy this circuit. And what we want to do is collapse these resistors into a single resistor to be able to find that current I. So we have the reciprocal of the equivalent resistance of the parallel resistors is equal to 1 over 6 ohms plus 1 over 3 ohms. So this will give 1/2. And therefore the equivalent resistance of these parallel resistors is 2 ohms. So we'll collapse these into a single resistor with a 2 ohm resistance. And now we'll copy this circuit again, and we have the equivalent resistor and the left resistor in series. So therefore the equivalent resistance of those resistors in series is the sum of the individual resistances, which is 7 ohms. So we can also collapse these into a single resistor, having a resistance of 7 ohms. And now we can apply Ohm's law, being the current by the resistance, to determine the current I. So turning this equation around, we have the current is the voltage on the resistance. So that gives 1.714. And let's add another decimal, and the current is in amps. So now we can work our way back to our previous circuit. So now we have the current through each of those resistors as 1.7143 amps. And therefore, using Ohm's law, we have the voltage drop across each of those resistors as the current by the resistance of each resistor. So on the left, we have 1.7143 by 5 ohms, which gives 8.5715 volts. And on the right hand side, we have 1.7143 by 2 ohms, which is 3.4286 volts, being the potential drop across the second resistor. So therefore, we now have the voltage drop across the first resistor and across the second set of parallel resistors, which we treated as an equivalent resistor. So that will be 3.4286 volts across each of those resistors, because they're in parallel. And we have the current through the left resistor, which is 1.7143 amps. And let me make a bit of room here. So using Ohm's law, we can find the current across each of those resistors in parallel. So that will be I is the voltage on the resistance. So in the top resistor, we have 3.4286 volts divided by 6 ohms, which gives 0.5714 amps. And then in the bottom resistor, we have 3.4286 on 3, which gives 1.1429 amps. So if you sum these two currents together, that's equal to the current coming in, which you can do as a check. And now we can calculate the power dissipated as heat in each resistor. So that will be the current by the potential drop across each resistor. So if you multiply the current by the voltage drop across each resistor for each of those resistors, you get the following values for the power dissipated as heat in each resistor. So 14.6941 watts. And then for this resistor, you get 3.9185 watts. And then for this resistor over here, you get 1.9591 watts. And now the power supplied by the battery is the current I by the electromotive force, which is 20.57 watts. And if you sum up the power dissipated in each resistor and take two decimal places, you're going to get the same result. So effectively, if the resistors are dissipating 20.57 joules every second, then they must be provided with that same amount of power. Now if you attach a voltmeter between point A and point B, what is the reading? Well, remember that we don't consider the resistance of a wire, which we treat as negligible compared to the resistance of the resistors in the circuit. So therefore the voltage drop between these 2 points is really the same as the voltage drop across this first resistor, which is 8.57 volts. And that's the reading you'll get on a voltmeter, which is connected in parallel to this resistor.